Hi everyone! So the focus of my presentation is on the anatomy and the function of the hypothalamus pituitary adrenal or HPA axis. I also plan to discuss the effects of early life adversity or early life stress on the HPA. The HPA axis is one of the core stress response systems. The literature suggests that early life adversity may produce an ongoing dysregulation of the HPA axis, which can result in elevated or blunted levels of cortisol and changes to the hippocampus. Studies have shown that these neurological changes could lead to many mental health issues, such as mood disorders, anxiety disorders, and post-traumatic stress disorder. The hypothalamic section of the HPA axis is formed by inhibitory and excitatory inputs, which are contained within the hypothalamic paraventricular nucleus, or the PVN. Brainstem nuclei, such as the nucleus tractus solitarius, send information about the body's physical state to the PVN and activate the system when the body experiences a physical stressor. The amygdala, bed nucleus of the stria terminalis, and prefrontal cortex are involved in carrying information about psychological stressors through the multisynaptic inputs. Then the paraventricular nucleus of the hypothalamus releases stressor exposure triggers corticotrophin-releasing hormone, or CRH, and arginine vasopressin, AVP. The main balancing hormone of the HPA axis is CRH. After exposure to an acute or chronic stressor, CRH is stimulated within seconds. CRH is then moved to the anterior pituitary gland where it activates adrenocorticotropic hormone, or ACTH. ACTH then creates and releases glucocorticoid hormones and acts on the adrenal cortex to quickly suppress activity of the HPA axis. This allows cortisol in humans and cortisone in rodents to return to baseline levels. The level of responsiveness of the HPA axis is regulated by feedback loops. These feedback loops return the system to homeostasis and act within the pituitary, frontal cortex, amygdala, hippocampus, and hypothalamus. This regulation should produce adaptive responses to social and psychological stressors, preparing the organism to anticipate and respond optimally to threat, but returning efficiently to homeostatic balance when the organism is no longer challenged. Cortisol is the end product of the HPA axis in humans. Cortisol levels can change dramatically within an individual and between people. In healthy humans, cortisol levels are elevated in the late evening, and cortisol continues to rise until about 30 minutes after one wakes up. Then cortisol is slowly reduced throughout the day. Cortisol contributes to many modifying physiological changes. For instance, cortisol plays an integral role in preparing humans to meet the potential energy demands connected to a stressful event. These include, but are not limited to, heightened attentiveness to a threat and readiness to respond defensively. Repeated or prolonged cortisol elevations can damage the body in a number of ways, so methods have evolved for downregulating the HPA axis under conditions of chronic cortisol activation. When humans and animals experience chronic stress, they initially have repeated and extended elevations in cortisol. This is then often followed by suppressed levels of cortisol and attenuated reactivity. The regulatory changes of the HPA axis and alterations in cortisol levels in particular have long been considered a primary mechanism through which early life stress is translated into physical and psychiatric disease across the lifespan. Early life stress such as violence, sexual abuse, and household instability have been associated with both heightened and blunted cortisol concentrations. Additionally, cortisol has been shown to be a factor in predicting mortality in patients with depression. Although genetics are an important factor in how well the HPA axis functions when exposed to early life stress, studies have shown that early caretaking environment also plays a considerable role. Adverse paternal parenting behaviors have been linked to elevated cortisol reactivity in infants and heightened cortisol levels in toddlers. In one study, the combination of low father involvement in infancy and high cortisol reactivity at age 7 prospectively predicted increased mental health problems at age 9. Furthermore, elevated HPA reactivity, heightened morning cortisol, flatter diurnal cortisol slopes, and alterations in autonomic and brain electrical activity have been discovered in adolescents with depressed mothers who are not medicated. Heightened cortisol has also been found in the saliva of children who have experienced maltreatment and who show symptoms of depression and PTSD. Additionally, a dairy study found that children in middle school who experienced excessive conflict with their caregivers were found to have heightened levels of cortisol in the evening, with a flatter diurnal slope and escalated cortisol throughout the day. Rodent studies have shown the impact of maternal interaction and maternal separation on the development and regulation of the offspring's current and adult HPA system's response to stress. When the mother is kept separate from the pup repeatedly or for extended periods of time, over 3 hours, researchers have found an increase in plasma levels of ACTH, exaggerated or attenuated HPA axis activity, and exaggerated glucocorticoid reaction to consequent stressors. Researchers have also found changes in corticotropin-releasing factor ribonucleic acid expression, greater instances of anxious behaviors and hypervigilance, moderate impairments in cognition, and fewer glucocorticoid receptors in the hippocampus in association with maternal separation. The physiological changes brought on by maternal separation last well beyond the separation period. Conversely, attention from the mother, such as maternal licking and grooming, has been shown to balance ACTH activity. Within the hippocampus, there are a number of structural and functional brain differences which are associated with maltreatment. The hippocampus is a structure of gray matter which resides within the limbic system and plays an important role in learning and varied aspects of memory. In animal studies, researchers have found chronic stress affects the hippocampus through excessive release of CRH, glucocorticoids, and glutamate. Additionally, overall hippocampal volume has been shown to positively correlate with age of trauma and psychopathology severity, particularly in externalizing behavior. There are a number of other neurological effects that early life stress can have on the brain. Early life adversity may cause impaired long-term potentiation induction, inhibition of brain-derived neurotrophic factor, and delays in myelination. Early life stress can also cause inhibition of neurogenesis and accelerated neuronal loss. Often these neurological changes are not seen until later development. For instance, preclinical studies have shown that differences in hippocampal synaptic density arise in rats exposed to early stress only after puberty. In closing, early life adversity can have lasting physiological and psychological effects. Countless studies have shown elevated or blunted cortisol levels and structural and functional differences in the brain of maltreated compared to non-maltreated children. These alterations can result in many mental health issues such as mood disorders, anxiety disorders, and post-traumatic stress disorder. It's clear that while genetics can have an influence on an individual's level of resilience, early life stress can play a considerable role in the dysregulation of the HPA axis in humans and animals. Adrenocorticoid and exaggerated glucocorticoid internal interaction potentiation induction inhibition an aminal in the aminal studies. Okay.